Okay, what we're going to do at this point is dive into how to implement concurrent and non-concurrent collectors with a little more detail. And we've already talked about implementing non-concurrent collectors, so the emphasis here will be on concurrent collectors. And as you may notice, the grad student version of the current assignment has you implement a concurrent collector, whereas the undergrad version has you implement a non-concurrent collector. And I'll kind of talk about that as we go through the example, and you'll see how to compare and contrast these different approaches. So, a little recap. Just recall, what is a collector? A collector is an interface that can be implemented to accumulate elements in a stream into a so-called mutable result container. And it should come as no surprise that the purpose of this is to be used with collect. Collector implementations can either be concurrent or non-concurrent based on the characteristics that you set as part of the characteristics factory method, which is essentially a way to set the metadata. The distinction between concurrent and non-concurrent only matters for parallel streams. So if you have a sequential stream, then it doesn't matter which one you use. It's going to be sequential. It's kind of overkill to use concurrent collectors for a non-concurrent. For a sequential stream, it's overkill to use a concurrent collector, as we'll discuss. But it doesn't matter. For a parallel stream, it matters. And so you have to be aware of the distinction. So as a result, a non-concurrent collector can be used for either a sequential stream or a parallel stream. Nobody here probably remembers this, but back in the day, there was a funny Saturday Night Live skit with Chevy Chase where they talked about the Shimmer non-dairy floor wax. And they said it was like a dessert topping and a floor wax, right? So it was able to do multiple things. So a non-concurrent collector is like the Shimmer non-dairy floor wax. You can use it for multiple different things. So remember that these non-concurrent collectors operate by merging subresults, as we just talked about before. The input source is partitioned into chunks. Each chunk is processed in parallel, and then the results are collected into a mutable result container, such as a list or a map or an array or whatever. And the different threads will operate on different instances of these intermediate result containers. So these are the intermediate result containers. Each of the things will be created, and then the results will be kind of merged together. And the subresults, these things, are then joined together into what is ultimately a final mutable result container. And as I said before, only one thread in the fork join pool is used to merge these together. And you kind of know how that works because you've written code that uses fork join directly. As a result, because there's only one thread, you don't need to have a synchronizer. So that's good. So this process is thread safe, and it's also order preserving. But merging can be costly for certain kinds of containers. In particular, maps and sets are expensive to merge because you have to do some kind of tree search or some kind of hash or whatever. It's not as simple as just tacking something at the end of an existing list or an existing array. So things that just do concatenation, that's really simple. But things that have to merge into a data structure that uses ordering or hashing or something like that, that's going to be a lot more complicated. So it's going to be more costly. So what's the alternative? And when should you apply the alternative? So the alternative here is a concurrent collector. And what the concurrent collector does is it creates one and only one mutable result container. Instead of all these intermediate result containers that have to be merged together later, it only makes one mutable result container. And then all the different threads that are running as part of the fork join pool in a parallel stream will accumulate the elements of the stream directly into that one and only container. So it's going to go directly to where it needs to be. It's not going to go ahead and be changing. As usual, the input source is partitioned into chunks. We've got these chunks. Each chunk is then collected, but it's collected into a single concurrent or thread-safe result container, which could be something like a concurrent map or a concurrent set, or in the grad student version of assignment 2B, it's the synchronized array. So synchronized array is basically got locking, so you can have multiple threads adding stuff to it without corrupting the internal data structures and leading to race conditions. Different threads in a parallel stream will share this one and only concurrent result container. So why is this good? The reason it's good is because there's no need to merge intermediate subresults. Instead, it's all just going directly into the one and only place to start with. And as a consequence, encounter order is not going to be preserved, most likely, unless really strange things happen. Because it's whatever the order in which the processing is done, that's the order of things are going to get stuck into the mutable but thread-safe concurrent result container. So when would this be a win, right? Remember, we can use non-concurrent collectors, we can use concurrent collectors for parallel streams. They all work semantically the same, or mostly the same in terms of leaving aside order-preserving stuff. But why would you ever want to use a concurrent collector? It's obviously got to have something, some reason to exist. And the reason is if you have data structures with collections with high merging costs. So if you have high merging costs, if it costs a lot to merge stuff, then we don't want to merge. We want to just put it directly into the final location. And you can take a look here at the EX14 folder in my GitHub repository for an example of this. And it has a really cool little helper class that I wrote, which I'll talk about in a second, called concurrent hash set collector. So hopefully everybody knows kind of what a concurrent hash map is, or concurrent map. Concurrent hash map in Java is basically a collection where multiple threads of control can put and get stuff into the collection without having to worry about race conditions. And concurrent hash map is super duper optimized with respect to synchronization. Very, very clever implementation. Concurrent hash set is simply a little wrapper around a concurrent hash map that gets rid of the key value pair and just has a set of keys. And under the hood, it uses concurrent hash map, so it's got all the other good stuff about that. It just defines a simpler interface. And the concurrent hash set collector is an implementation of a collector that works for concurrent hash sets. And as a result, you can use it in a context where you need a concurrent collector because it uses the concurrent hash map's ability to add things into the hash set / map very efficiently, even in multiple threads of control. So again, why would you use this? Well, if you try to use hash maps, merging hash maps is expensive because you've got to take the two, you have n intermediate results, and you've got to then take all the contents of one and hash them into the contents of another. And that just hashing overhead is non-trivial. It's got a high constant factor, to use algorithms and data structures lingo. And in contrast, putting things into a concurrent hash map is very fast because it's super optimized to do this with low contention, and it uses compare and swap operations and other things to minimize the overhead of this. And it also has this really clever approach where it tries to partition the hash table so that oftentimes when things are hashed into the hash table, they are hashed to different portions of the hash table. That's what a good hash function does. And they're actually different locks that are used for different portions of the hash table. So it's, in many cases, you will have no contention at all, because if two values hash to two locations in two different threads, there will be no contention at all because there's not a single place where they're being stored. And you can take a look at this article that'll talk about a bit about concurrent hash maps. It's also worth noting, by the way, just as an aside, there's also something called a synchronized map in Java. And a synchronized map, for those of you who are doing the grad student version of synchronized array, synchronized map is pretty much like synchronized array. It simply is a synchronized wrapper around the unsynchronized map abstraction, where there's a single lock, and therefore multiple threads will end up competing to access that single lock to update the map. So that will be much slower in a multi-threaded environment, typically, than a concurrent hash map where you can have multiple threads with multiple locks, so they don't actually contend for each other. So anyway, just a little bit of side discussion about the cool concurrent hash map collection. So now let's show how we can implement a concurrent container, so concurrent collector. Recall again that there are three generic types you can have for collector, or you must have T, A, and R, which are actually more informative than they appear at first glance. So T is the type of object, or type of the objects that are available in the streams, or maybe the better word is type of elements available in the stream. And that would be things like integer, string, search results, whatever. A is the type of mutable accumulator object for the collection, concurrent hash set, an array list, and so on. And R is the type of the final result, which is, again, concurrent hash set, array list of T, or whatever. There are 5 methods, just like there are for non-concurrent containers. There's characteristics, where we have unordered, which says not to preserve in counter order. Concurrent collectors should be unordered because they're going to be done from different threads, so you really have no way to enforce the encounter order, or no simple, efficient way. A non-concurrent collector could be ordered if there's no overhead for that. For example, if you use the combiner portion of the collector and you simply have like an array list, you can simply append the right-hand part to the left-hand part, and it will obey the encounter order. Identity finish basically just says, is the finisher method necessary or not? If you have identity method, then it's unnecessary, otherwise it's necessary. A concurrent collector should be identity finish because there is no, you're putting everything into the mutable result container. When you're there, you're done. Whereas a non-concurrent collector could be. And then, of course, the final characteristic is concurrent. And that just says, is the accumulator called concurrently from multiple threads? And if it's a concurrent container, a collector, it better be, that better be set. And that also implies you have to synchronize the result container. So concurrent collector, of course, should be concurrent, otherwise it's not a concurrent collector, whereas the non-concurrent collector should not be concurrent, because otherwise chaos and insanity will result. If you have a concurrent collector, the combiner method should be a no-op, since it'll never be called. Because remember, the combiner is only used to merge together intermediate subresults to make a new subresult or a new final result. So you can use non-concurrent collectors with either sequential or parallel streams, but we're going to focus on concurrent collectors here. And as we talked about before, here's how you can do this. Make sure when you're implementing your assignment 2B that you look carefully at the syntax for how this works. Okay, so let's take a look at the methods, and we'll show how you'd implement them for concurrent collections. So supplier, that's the factory that returns an instance that's used to generate an empty result container. Typically, again, some kind of method reference or constructor reference is usually what's done there. So if you have a non-concurrent collector, then you could just say, return array list, : new. And that will have a result container, an array list, for each of the various threads in the parallel stream. Conversely, a concurrent collector, like concurrent hash set collector, needs to return a means of being able to make a new concurrent collection. So in this case, we would return a constructor reference to concurrent hash set if we're doing the concurrent collector. And that'll make the appropriate kind of thing. And in that case, just recall, there's only one result container that's shared by everybody in a parallel stream. The accumulator, again, it returns a by consumer that will add a new element to the result container. You could have array list add, or you could say array : add in order to make this work properly. Or you could say, concurrent hash set : add. Again, if you use this approach, then that method darn well better be synchronized. Otherwise, chaos and insanity will result. So make sure you give back the right kind of method reference here, depending on what it is you're trying to do. Remember, by the way, when you return a method reference, you don't have to say return new concurrent hash set : add. You just say return concurrent hash set : add. And it knows how to do the magic to convert that into something that matches the result, the by consumer that's expected here. Combiner merges the operations, that merges the results together, the intermediate results together. So if we were doing a non-concurrent collector, then this would be an example of how to merge, right? So you have one list and another list, and we add another to the one. We basically append this to the end of that, and then we return the first one. If you have the concurrent characteristic set, then it just is a no-op. So you just return null. And then finally, finisher, that's the thing that returns the result container for the final result type. And so it could be various things, depending on what you're trying to do. For if you have the identity finish characteristic set, then you should make this a no-op. And that's the end of that. At this point, I think most people figured this out already, but at this point, you should know everything you need to know to implement the array collector for your assignment. Keep in mind that for your assignment, the way that we make this work, the code is actually very similar for both the grad and the ungrad version. The difference being that the undergrad version is a non-concurrent collector, so it can use the unsynchronized array, whereas the grad student version is a concurrent collector, and it uses the synchronized array. And because it's concurrent, therefore its accumulator method has to accumulate directly into a thread-safe or synchronized mutable result container, which would be an instance of synchronized array.